This is Physics 1020-1090, a lecture for Wednesday, April 15th. Chapter 30 on nuclear energy, but this is a fourth video where I want to kind of just wrap up the entire semester. So basically, when I said at the end of video 3 that we're going to go on and discuss the practice exam, I lied. This is going to be one more short video just wrapping up the semester. So here it is. We started the semester talking about electrostatics. That is the electric fields, Coulomb's law, electricity properties. And then we went on and we talked about magnetostatics or magnetism. And then we put the two together and found that we could talk, they were really one theory, electricity and magnetism, E&M. And when we put the ideas of electricity together with the ideas of magnetism, we got that you could actually have electromagnetic waves. That is, waves of electromagnetic energy that would propagate, and it propagated at the speed of light, so that light was an electromagnetic wave. It's one of the key concepts that I really want you to remember. Now, we talked about a lot of different things with electricity and magnetism. We talked about how motors work, electric motors, how generators work. We talked about circuits in general and things like speakers and microphones and transformers. The entire world that we live in is driven by electricity and magnetism, and I hope you get some appreciation of how those sorts of properties impact the world we live in, because we truly live in an electrical world. And then once we figured out the electromagnetic waves were a form of light, we could talk about the entire spectrum of electromagnetic waves, because they could have different frequencies and different wavelengths. And that brought us then to the question of optics. Optics is the properties of light. And again, we've talked about some very practical things like how mirrors and lenses work. And we use that to understand things like telescopes and microscopes, the compound microscope. And then we went further and we talked about the wave nature of light, and we talked about wave optics, and particularly Young's experiment, and how the wave nature can play a role in things like interference and diffraction. And we went on and we talked about modern physics. So electricity, magnetism, and optics is basically 19th century physics, the 1800s. Modern physics is more 20th century physics, the 1900s. And we talked about, first, relativity. Well, we didn't talk about relativity much because we lost that day and we skipped that chapter. But relativity really grew out of these ideas of electricity and magnetism. And, of course, the key concept in relativity is things can't move faster than the speed of light. So light played a role in the development of relativity. And then we went on and talked about quantum physics, both the quantum physics of light, that is, light not only acts like a wave, but it also acts like a particle. And then we talked about the quantum physics of particles. Particles aren't just particles, they also have wave properties. So the development of relativity and quantum physics were two of the greatest accomplishments of 20th century physics. And then we went on to talk about atomic structure. And when we talked about atomic structure, we were mainly talking about Ernest Rutherford and Niels Bohr and their contributions. And really this chapter here got us to the edge of talking about chemistry, because some of the sections that we didn't spend much time on were really talking about multi-electron atoms, and that's really the basis of chemistry. So we got right up to the edge of chemistry with looking at atomic structure. And then we went on and talked about nuclear physics. And we talked about it in a couple contexts. First of all, we just talked about how nuclear physics works. We talked about it in a historical context, because I think it's important that you realize that the history of nuclear physics really parallels the history of the first half of the 20th century. And these ideas for nuclear physics are not just academic concerns. They are with us every day. For instance, we hear about North Korea or Iran developing nuclear weapons. We're talking about they're developing using these ideas from nuclear physics. When you often hear about Iran starting up its centrifuges. Well, what they're talking about is they're using centrifuges to separate uranium-235 from 238 in order to build then atomic weapons. So these ideas from modern physics not only are interesting intellectual exercises, they affect our everyday life. So I want you to get an idea how important these topics are that we discussed. Okay, now we also discuss some about the scientific method. And we didn't have a lot of homework problems or a lot of test problems about this, but I think it is one of the most important things we talked about. And especially we talked about the several key experiments and how you develop a hypothesis. For instance, Millikan wanted to test the hypothesis that charge came in discrete amounts. Electrons had a fixed charge, and he did what's known as the oil drop experiment, which we discussed, and showed that his data was consistent with the idea of electrons have discrete amount of charge. Faraday, Michael Faraday, we talked about his experiments on electromagnetic induction. In fact, we did a couple of them in class, and how Faraday had the hypothesis that changing that magnetism could produce electricity. Basically, we found changing magnetic fields could produce electrical currents. So Faraday tested that and was able to show that in his experiments. We talked, perhaps one of the classic experiments of all of physics was Young's experiment, his double slit experiment, where he really demonstrated the wave nature of light. Remember, the scientific method, he had a hypothesis that light was a wave. He came up with a key experiment that would test that hypothesis. He performed the experiment, and he found that his results were consistent with the wave nature of light. And we went on and we talked about perhaps one of the greatest experimentalists of all time, Ernest Rutherford, and his experiments. He had several. He did his experiment that we really talked about quite a bit was his fired alpha particles and a gold foil, and from the scattering was able to deduce the nuclear structure of the atom. So in this case, it's the scientific method. He maybe didn't have the hypothesis right at the start, but he did an experiment, and from his experiment, he gained a hypothesis of the nuclear structure, and then that would lead him to additional experiments where he could verify that. So Rutherford's experiments. He had other experiments too. He had an experiment, this beautiful experiment, where he figured out that alpha particles were helium nuclei. By letting the alpha particles go into an enclosed container, they picked up some electrons, and then he had helium gas inside the thing. We talked about his experiment where he did the first man-made nuclear reaction, and how he did all those different controls in his experiment to verify that what was happening was the nitrogen atom was being disintegrated. So these were key experiments that really hopefully illustrate the scientific method. Sometimes the scientific method is this very organized method that we talked about. Sometimes it's luck, like Röntgen. When he had his electrons hit the glass, and he sort of accidentally discovered that there was some X-ray, some radiation given off. He discovered X-rays. So it's not always that simple. And finally, another classic example of the scientific method at work was fission. Fission is an example where you had a hypothesis that that was wrong. That the uranium nucleus was giving off a couple of alpha particles, but they did the experiments to test it, and the experiments forced them to come to a different conclusion, that the uranium nucleus was splitting into two. Another example is the discovery of the neutron by Richard Chadwick, who worked in Rutherford's lab. There was a hypothesis that when you fired protons, or you fired alpha particles at beryllium, the hypothesis was you were producing gamma rays, electromagnetic radiation. But Chadwick was able to show through his experiments an alternative hypothesis was correct, that you were actually producing neutrons, and he discovered the neutron. So I want you to get the idea that science doesn't proceed by just coming up with these ideas sort of the seat of your pants. Scientists, sometimes the initial hypothesis is a creative act, but the hypothesis is tested rigorously through experiments, and ultimately experiments decide what was correct, what's true, and what isn't. That's the essence of science, and I hope you got that from this semester. Finally, one of my heroes in science is Isaac Asimov. He was a science writer. You might notice that some of the books on the shelf behind me is my Asimov collection. He was mainly known as a science fiction writer. He wrote like the short story Nightfall was one of his famous stories. He wrote a collection called I, Robot about the 3 laws of robotics that has influenced the world since. He had a wonderful trilogy called the Foundation Trilogy, which is considered one of the greatest science fiction trilogies of all time. And finally, he wrote science fact. He wrote science popularizations, and one collection of science essays was Adding a Dimension. And in this essay, and this is the reason why I bring him up, he came up with what is known as the Isaac Awards. He claims he named these the Isaac Awards after Isaac Newton, but Isaac Asimov, we can guess who he really named the awards after. But he was the greatest scientist of all time. So here is Isaac Asimov's 10 greatest scientists of all time. I want you to see which ones we've talked about in this semester. Let's go through them. Archimedes. He was a Greek scientist who almost discovered calculus, made some great contributions in very early times. We didn't talk about him. Charles Darwin discovered evolution. We didn't talk about him. Albert Einstein we certainly talked about, and would have talked about even more had we done the chapter on relativity. Michael Faraday we talked about with Faraday's law of induction, one of the people who's key in our discussion of electricity and magnetism. Galileo we didn't talk about. Lavoisier, one of the early father of chemistry, really, we didn't talk about. But Maxwell, we talked about the prediction of electromagnetic waves. Isaac Newton, mainly Isaac Newton was discussed in your first semester of physics, but we talked about him here when we were sending light through a prism and got a spectrum of colors. That was some of Newton's work. We talked about the reflecting telescope, which Newton invented. Louis Pasteur we didn't talk about in our semester, but Ernest Rutherford, we talked about definitely his experiments. So let's count them. 1, Einstein, Faraday. 2, Maxwell. 3, Newton. 4, Rutherford. 5 out of the 10 greatest scientists of all time were scientists that you talked about and we talked about in this class. And I would argue that you could throw out Archimedes and replace him by Niels Bohr and you'd have a better list. And if you did that, we'd have 6 out of the 10 greatest scientists you got to talk about in this semester. So hopefully you'll go away realizing that the physics that we talked about is really some of the greatest physics ideas and most important science that you're ever going to discuss. All right, so that now is our summary, and the next lecture will indeed be going over the practice exams.